problem sets for work problems. We have 9 problems that we're going to go through very quickly. Pause is going to be your friend on this video. We're going to go very quickly on these. That way, if you get stuck on one of these problems that we give you, you'll be able to go back and take a look and figure out how to do it. Now, what Coach Mudd and I suggest that you do is you attempt the problem, struggle with it, and if you can't figure it out, give yourself just enough hint, hit pause, and keep struggling through it. The best way that you're going to work some of these problems is by struggling through them, and then you'll start figuring them out. And then, hopefully, by the time you get 2 or 3 problems into this, they should be easy to do and you won't have to watch the rest of the video. So let's get started. Here is number 1. A force of 800 newtons is needed to push a car across a lot. 2 students push the car 40 meters. How much work is done? Now, what I want you to do, every time you do a problem, break it down into what is there, what is given, and what you're looking for. So, a force of 800 newtons. So the first thing I'm going to do is I'm going to write force equals 800 newtons. We're going to push the car for 40 meters. That is a distance, 40 meters. How much work is done? Does it give us an angle? No. So the angle is 0. And remember, the cosine of 0 is 1. We can forget the part of W equals FD cosine of theta. We can leave that part out. So we have 800 newtons times 40 meters. And for that question, we're going to get 32,000 joules. And of course, if we're going to do sig figs, the actual answer should be 30,000 joules. There's number 1. Number 2, how much work is done? All right, I'm going to start here. How much work is done in lifting a 60 kilogram crate? That's mass, 60 kilograms, a vertical distance of 10 meters. So work equals force times distance. Again, we have no angle here, so we assume that it's 0. Cosine of 0 is 1. But we don't have a force. But let's think about this. We're going vertically. Since we're going vertically, our force can be equal to the weight. So we're going to use good old Newton's second law. F is the same as mass times gravity. It's ma. F equals ma, but since we're specifically talking about gravity, we can put a g and then times d. So my mass is 60 kilograms. Gravity is 9.8 meters per second squared. And the distance that I'm going is 10 meters. Rat-a-tat-tat in your calculator, and you get 5880 joules. And that's right for the sig figs, 5880 joules. Number 3, a force of 600 newtons, force is 600 newtons, is applied to a metal box to pull it 15 meters. That's distance. The rope used to pull was held at an angle of 46 degrees with the floor. How much work is done? Well, now we have an angle. If I wanted to draw it, this is what it would look like. There's 46, and the force is 600 newtons. I know that's kind of hard to read, but that's actually what we're doing. The formula is force times distance times the cosine of theta. My force is 600 newtons. The distance is 15 meters. And I have the cosine of 46 degrees. I think you get 6251 joules. Or if we do this with sig figs, since 600 only has one sig fig, it's going to be 6,000 joules. Number 4, a 2 kilogram puck is accelerated at 5 meters per second squared, or 0.50 meters across a frictionless air hockey table. How much work is done? There's no angle. We assume it to be 0. Cosine of 0 is 1. So we have work equals force times distance. Well, they didn't give us a force, but Newton's second law says Force is mass times acceleration. So my mass is 2 kilograms. The acceleration was 5 meters per second squared. And the distance that we went was 0.50 meters. Pop that all into the calculator. And we get 5.0 joules. And that's correct for the sig figs. That's number 4. We're back with number 5. These are the work problems. Number 5. A car has run out of gas. Fortunately, there is a gas station nearby. You must exert a force of 715 newtons on the car in order to move it. By the time you reach the station, you have done 2.72 times 10 to the 4th joules of work. How far have you pushed the car? Well, there's no angle, so therefore the angle is 0. Cosine of 0 is 1, so we can ignore that part. Work equals force times distance. Now here it depends on how you want to solve it. You can either rearrange this formula right here, do the algebra ahead of time, or if you would rather plug in the numbers, and it doesn't matter. Oops. This is not the way that I normally do the problem, so force times distance. Divide both sides by 715. So my distance is going to be 38.0 meters. You get the exact same answer because we have work divided by force. It's the exact same answer. I just like to rearrange my variables. That's number 5. Number 6. An applied force of 20 newtons accelerates a block across a level frictionless surface from rest, so VI is 0, to a velocity VF of 8 meters per second in a time of 2.5 seconds. Calculate the work done. Okay, there's no angle, so the angle is 0, the cosine of 0 is 1. I know I keep saying that, but you always need to look for that angle because the formula is work equals force times distance times the cosine of theta. So we don't want to forget about the cosine part. We have a problem here though. It asks us for work. We have a force, but we don't have a distance. You got to think way back to those kinematics problems that we did. With VI and VF and T, we can figure out D. And there are a couple different ways that we can solve this. This is the way that I chose to do it. The first thing that I decided to do is find the acceleration. Well, the acceleration is the change in velocity over the time. So I have 8 meters per second minus 0 over 2.5 seconds. So my acceleration in this case is 3.2 meters per second squared. Then, that's step 1. Then I remember a formula that says distance equals VIT plus 1/2 AT squared. Well, since VI was 0, that part goes away. So I'm left with 1/2 A, which I just found, 3.2, times T squared. Now, just like before when we did kinematics, don't forget the square. It's very easy to do and a lot of people do it. Don't forget it. So the distance that this thing went was 10 meters. Okay, that was part 2. Now, I have a force and I have found the distance. So work equals force times distance. What was my force? 20 newtons. What was the distance? 10 meters. So the work is 200 joules. Number 6. Number 7. A gardener pushes down on the handle of a lawnmower at an angle of 45 degrees with an applied force of 141 newtons. While pushing the mower 8.2 8.5, that's a D, 8.5 meters along the ground. Calculate the work done. Now we have an angle. The reason why I kept saying don't forget that cosine of theta, when we have an angle we have to make sure that we use that. So the force was 141 newtons. The distance was 8.5 meters. And the angle was 45 degrees. So this gardener did 847 joules of work, or with sig figs, 850 joules of work. That's number 7. Number 8, a building under construction requires an amount of cement to be lifted 76.2 meters by a crane. If the net work done on the cement is 1.31 times 10 to the third joules, what is the magnitude of the net force? Since we're going vertically, we have no angle. The angle is 0. We can ignore that because the cosine of 0 is 1. Okay, I want to know the force. I'm going to do it the way I normally do it. Rearrange the variables and then plug in. So the amount of force is 17.2 newtons. That's number 8. And number 9, kind of tricky. Classic question, might show up on the 6 weeks test, something very similar. A student librarian picks up a 0.95 kilogram book from the floor to a height. So my original height, I can either call it H or I can call it dy, it doesn't matter, 1.25 meters. She carries the book 8 meters to the shelves. So that's going to be my distance in the x direction, and places the book on a shelf, which again is at a height of 2 meters. How much work is done on the book? Okay. Here's the trick. I've got a floor. I lift the book up to a certain height, then I carry it across the floor, and then I lift it up to another height. Think human horsepower lab. Think human horsepower lab. Where was the work done? Did I push the book across the floor? No, I didn't. I lifted the book. Here was 1.25, and then the entire height was 2. So the distance in the vertical direction that I actually lifted this book was 2 meters. So that's what I'm going to use. What is the force? Well, in this case, since we're doing vertically, the force is going to be the weight, which we remember is mass times gravity. Remember Newton's second law, it's mass times acceleration. But because it's weight, we're going to do a specific acceleration. That's the acceleration due to gravity. And then times the height there, d. dy, we can call it h. But we probably don't want to use h because later on when we talk about potential energy, we are going to be using h, but it's going to be the same problem. And you'll be able to see with the work energy theorem later on how they relate. So since it's mass times gravity times the height, 0.95 kilograms times good old 9.8 meters per second squared times that height of 2 meters. The actual work that was done on the book is 19 newtons. I did that again, 19 joules. This has been a Mudborough production, copyright 2013. Have fun working problems.